哎，
想要送这个邀请函给你，就是我们的，就是这个小 B 点是办在第17
哦，
周的。
你是学士班的。
哦，我是电机系的。
哦，你，哦，对对对对，好好好。
对对对对，然
好，
后我们是办在就是第17周的礼拜六。
这谢谢你的邀请啊。
对啊，那老师可以收这个邀请函啊，或者说
好，
老师如果要我再寄一封 email 也给你，也是可以，看看要不要，都可以。
哎。All right. So how did you like yesterday's exam? I saw some people turn it earlier. Yeah. Okay, that's good to know. And so 刚刚看了你们打牌，我觉得还蛮特别的啊。It's probably it's been a long time since I last saw any student playing the poker cards, playing cards. In my generation, we carry poker cards all the time. That's all we do. No cell phone, no whatsoever. So we typically play. Typically, if we can find four people, we sit down and play the poker cards. Were you playing bridge or something? No. Yeah. It's been a long time since I known any student who played poker pie. So good for you. Um, my partners, yeah. So I was a freshman, 大一的时候, and we carried playing card all the time. And there were four people three other people that played with me a lot. One is Professor 郑贵忠. Any 专题生 here? Yeah, Professor Jing, raise your hand. Yeah. And the other is a professor with NTU CS department, Professor Lin Shoude, Wang Mei所的. Yeah. So 3 out of 4 people eventually became a professor, and because why we playing card together, because we had no friends. We were losers, right? Nobody liked us, like more the handsome guys. They all joined clubs, and we are like the outcast, 就是边缘的啊，所以才会在上课之间就打牌啊。不过你们看起来不太边缘呐啊。These people, do they have friends? Yeah. All right. Okay, so much about life reflection. 回忆我自己的人生啊。Do we have the screen? Yeah, we don't. Do we? Yeah. What's going on? Oh, cool. Yeah. Okay, so today I plan to continue the lecture from last week, which we didn't finish. And in that lecture, not this one, but the 7th one. In the 7th one, we were talking about design, right? I suggested that when we design a digital filter in discrete time, one way of designing is to borrow from analog. Okay, that's a good principle, to borrow from analog. Historically speaking, 历史上来讲, analog was there before digital, right? So way before people knew how to talk about frequency response in the continuous time domain. So we have the Laplace transform, and we can put together a circuit, if you will. You can put together resistors and capacitors and inductors, and they have desired frequency responses. You can design analog circuit, right? Design your analog response with components. So how about if we can just kind of, historically speaking, we can borrow from analog. That's a good starting point. So not just this in this lecture, we talk about this example. We will finish talking about this example of borrowing from analog by sampling the analog response. sampling the continuous time response. I mean the impulse response. Sampling that, the result becomes a digital sequence, right? And then from there, we can find the difference equation. Digital filter is all about difference equation, using difference equation, designing them, finding the right coefficients. So that's one example. We'll finish talking. And so a bit about the agenda. So today. So we'll keep talking about this example of trying to simulate this analog system with a capacitor and resistor. And we just inject a current I of t. We expect to measure that we can measure the output as a voltage dropping across the parallel connection of capacitor and resistor. Okay, and this we know is what kind of filter is this? When we approach high frequency, right? When you approach high frequency, the capacitor becomes what? Becomes a short circuit, right? So we know that this is a low pass filter because at high frequency, the voltage will approach zero. Okay. So this is we know that it's a low pass, and we know that the corner frequency, there is an important factor called RC time constant, right? RC time constant. And we expect that if we plot in this course, we use big omega to describe frequency in the continuous time. Okay, and we know that around it, there's a corner frequency of omega 0 defined as 1 over tau. There's a corner frequency, and if I remember correctly, we see a 3 dB drop of gain. Okay, and so gain is dropped by 3 dB, and then it should keep dropping. There should be a 6 dB per octave if we take the log of omega. Okay, it should be a straight line here and log of the gain. Okay, let's say gain is roughly speaking log h. Yeah, log 10 doesn't matter. Log scale, in log scale, we see flat gain, roughly flat, high gain before the cutoff corner frequency, and then after that, the gain should keep dropping at the rate of 6 dB per octave. I hope that many of you might be familiar with this concept when you study circuits and analog design, stuff like that. The corner frequency, and this is a low-pass filter for sure because of the nature of capacitor and resistor, right? But when we borrow this, in this lecture, we say our suggestion goes that we go back to the time domain. Okay, this is frequency domain. When you go back to a time domain, we see the impulse response. The impulse response should be, there is a kind of a peak amplitude at time zero, and then it decays at a rate of 1 over tau. Okay, so the impulse response can be written as h of t equals the peak. Actually, the peak should be 1 over c, something like that. Okay, charge accumulation, but it's not that important. The peak response times exponential decay minus alpha t, where alpha is, let me say just t over rc. Yeah. Times, if you will, times the unit step function. Okay, that's our zero is a causal system, 0 before time 0. Okay, so this is the analog impulse response we want to sample. Okay, so our suggestion last time is that when you design a kind of equivalent digital system, you may want to just sample the impulse response in continuous time, so that the resulting sequence is a discrete time sequence happening in discrete time. So we suggest that, hey, maybe let's define our design as if we were, let's put a C right here to emphasize this is continuous time. Okay, this is not the C. That is the capacitor. Right? Continuous time. Hn, we will sample Hc at n times a sampling period. Okay, and then for certain reason, we also recommend adding the factor t right here, so that when we come back to our handout, last time I spent some a few moments to explain that when we do this, when you're after applying this sampling of the impulse response, the resulting sequence becomes an impulse response of a digital system. Okay, and this impulse response, how do we use it? We are going to convolve with it with any digital input, and then the system produces an output, right? Convolution. So last time I spent a few moments to explain that when we convolve our input sequence, if our input sequence is denoted by x, if our input is denoted by x, and we convolve it with this h of n, which is the result from sampling the continuous continuous impulse response, then when we convolve them in discrete time, it's like a Riemann approximation of an integral. Yeah, the result is a sum of areas under these rectangles. That's just you can check that. Okay, so and we know that the sum of the areas in these rectangles is an approximation of the area under the curve. What curve? The continuous convolution. Okay, so in this way we can say that when we sample, when we suggest this expression, when we suggest this is a design, we have in mind that the resulting system should approximate an analog system in the sense of Riemann approximation. Convolution in discrete time will be similar, will be approximately equal to convolution in continuous time. Okay, if we know that the approximation will be good if we have sufficiently small t. That makes sense because Riemann sum will be good only if we just slice the time into small units, right? So you want that time unit, which is our sampling period, you want that to be sufficiently small so that we can obtain a good approximation. Okay, so that's the idea. Okay, so now, so that's what we had last time. But now we have a few questions. First, it's about implementation. How do we implement this idea when after sampling the impulse response, we get a sequence, right? But this is an infinite sequence. Okay? This is an infinite sequence. So how do we calculate the convolution of any arbitrary input signal with an infinite impulse response, or IIR, with an IIR? Okay, so fortunately, you will see that we can find a difference equation that does the job. Okay? Fortunately, we can find a difference equation that does the job. So implementation turns out to be pretty easy. And my second question is then, after we obtain the difference equation, then we can check if the system is stable, okay? And then if it is, we can talk about frequency response of the system, okay? So first thing first, how do we find that difference equation? 那个差分方程, how do we find it, okay? And it turns out to be pretty easy. So it should be pretty straightforward that h of n, now t is a factor, and then a is the peak of the impulse response. And then this is a result after sampling our impulse response in continuous time. Okay, so let me write down again, copy again that h of t, hc of t equals to a e minus alpha t, where, if you will, alpha is 1 over rc. Okay, right? So now we have this expression, and that's our expression. After sampling that impulse response, things become in the discrete time domain. And this sequence turns out to be again, the causality is preserved because obviously h of n is 0 before time 0. But then after time 0, it is a what? A geometric sequence. Okay? H of n is a geometric sequence, 是一个几何数列啊 geometric sequence, 等比数列啊 geometric sequence. Therefore, we know how to calculate h of z, right? We know how to calculate h of z because h of z then, therefore, h of z, let me put the parenthesis. H of z by definition is 1 plus, no, not 1, is the sum of h0 plus h1 z inverse plus h2 z inverse square and so on, infinite sequence. Okay, and now if you plug it in, you find that it should be pretty straightforward that the result is this. We get this result. Okay, we get the result with a pole. With a pole and with the pole, yeah, this is just and the equality holds, or let's say the equality holds if for z outside that radius. Outside that radius, okay? Equality holds there. So the region of convergence for this h of z would be outside that radius. Which radius? We talk about this radius. This is a radius, okay? So you know that if we just, now the next job is to convert this expression. Now that we convert this expression, h of z equals to that, then what's the corresponding difference equation? Okay, it should be now pretty straightforward that the difference equation, and here we write it as h of z equals to b of z divided by a of z, according to our convention, our notation, bz divided by a of z, right? So b of z has only one constant term. B of z has only one constant term here, which goes here, right? And a of z has two terms, right? A of z now is a first order polynomial of z inverse. So therefore, this factor 1 goes here. And here, how about here? This parameter, just if you are careful about the sign, you're careful about the plus or minus sign here, we should have the factor of e to the minus alpha t, where alpha equals to 1 over RC, 1 over tau, okay? So this factor goes here, yeah, where alpha is 1 over RC. So far so good? So you can implement it. This is something that can be run on any sort of processor, okay? This is an equation you can use to produce your sample in a causal way. Given one path sample, given any path sample yn and the current input xn, make a linear combination and produce your output. Okay, you can implement it. So it's pretty straightforward. And it's also good to know that since this pole here, now we have a pole which is located at, we have a pole right here somewhere inside the unit circle. We have a pole which is inside the unit circle. Okay, and the distance here is e to the minus alpha sampling period. Okay, we have a pole inside the unit circle. Therefore, the region of convergence, so bad. This is hilarious. Drawing, is it really that bad? Okay, this is good. Okay. So our region of convergence, okay, let me add the imaginary axis on the z-plane. Yeah. So this is real z. This is imaginary part of z. Okay. So this is our z-plane, and we know that now we have a situation where our pole is inside the unit circle, right? Inside the unit circle. So that means the region of convergence should be outside this circle with radius with that radius. Okay, the region of convergence includes the unit circle. The region of convergence includes the unit circle if we use the difference equation in a causal manner. Okay, which is the manner I recommend. Okay, so sure, that means the system is stable and we can evaluate the Fourier transform. Right, the system is stable. Its region of convergence includes the unit circle. Therefore, we can evaluate the transform on the unit circle, which gives us the frequency response. Okay. So now the frequency response, if you will, the frequency response is something we can write down explicitly. Okay. So we can just refer to this result. This is h of z, and when we evaluate it on the unit circle. Should I repeat that? H of z is right here, right? Actually, let me just put a. This is h of z. And here we are evaluating it on the unit circle. It's an evaluation on the unit circle. Then we obtain the frequency response. Okay? The frequency response explicitly, 如果我们就是把它写下来 explicitly 的话，just write it down explicitly. TA divided by what? 1 minus e to the minus alpha t and e to the minus j omega. That's the inverse. Let's say omega now is between minus pi and pi. Okay? Around the unit circle. Around the unit circle. This is how we evaluate the frequency response. Okay? All right. So now we have some observation. We can have some observation. Okay? I'm actually having too much space. Yeah. Okay, let me move things around a little. Yeah. Okay. Get down. Wait. What's wrong? Get down. Okay. Shoot. So yeah, technology is too advanced for me. Okay. Get down here. This is the frequency response we have, right? We have this frequency response. Let's plug in a few numbers. Let's plug in, how about the frequency response, the gain at DC, right? Omega equals to 0. That should be the gain, our gain at DC, at 0 frequency, okay? So we check that, h of e to the j 0, yeah? Then obviously this is the result, okay? It equals to TA divided by this factor 1 minus something, and this, when at DC, this factor equals to 1, right? So this is our gain at DC, okay? Yeah, this is our gain at DC. And how about at Nyquist frequency, which means omega is pi? When omega equals to pi, that's the Nyquist frequency, half of sampling rate. This corresponds to half the sampling rate, okay? At omega equals to pi, which is our highest frequency, then we evaluate h of z at -1. At -1, then this changes sign. There's a change of sign. Okay? I'm pretty sure you can figure this out. So this is our gain at Nyquist, and this is our gain at DC. Okay? And how about any other frequency? Okay? For any other frequency, of course, you can just plug in any omega in this range. Okay? Any omega in that range, and this is what I want to emphasize. You can always factor our frequency response into the magnitude and the phase. Yeah, we need to know that. Okay, everybody in this classroom, please know this. Okay, let's agree that we will call the absolute value, call this part the magnitude response, which is a function of omega, and then the exponent right here, e to the j. This is the phase. Okay, the phase, and it is denoted by this angle sign, the phase. Okay, phase of our complex valued response. Okay, but always be aware that the frequency response is a complex function. Okay, it's a complex valued function. 是只是复数啊。Their values are always complex in general. So magnitude versus phase. So in terms of magnitude, so now let's make some observation. But when we plug in number at DC, our this should be at DC, this should be TA divided by 1 minus R. Okay, let's denote where R is defined as this e to the minus alpha t. Okay, yeah. So DC gain, I should take an absolute value, but you know that since R is less than 1, I don't really need to show the absolute value, okay? It's okay not to show the absolute value because I know R is less than 1. R is less than 1. Can we agree on that? Yeah. R is less than 1 for the system to be stable and it makes sense. E to the minus alpha t, right? Yeah. Always less than 1, okay? So this is a gain at DC. Gain at DC. But how about gain at, our gain, oh, okay, reading things. Our gain at Nyquist, right? There, so see that if R is so it depends on how large R is, okay? But in general, it's a smaller number. Yeah. At DC, the gain here is equal to TA divided by 1 plus R. Okay? And which, of course, is smaller than TA divided by 1 minus R. Yeah. So high frequency, the higher frequency has a low gain, lower frequency has high gain. And in between, you will actually, we can see that it's a monotonically decreasing. I'm not doing very good job, but it's a monotonically decreasing. Okay, it's a monotonically decreasing magnitude response that we have right here. Okay. Yeah, I hope I can do a better job, but you know what I mean. Yeah, yeah, it's actually monotonically decreasing. As frequency increases, okay, this function is monotonically decreasing. 严格减的啊 monotonically decreasing. So, yeah, with the highest gain of at DC and minimum or lowest gain at Nyquist, okay? But how much do they differ, right? Any suggestion, any observation, any conclusion you can kind of make? Remember that we say this is a good design when we have what, small enough or large enough t. T is the sampling period, right? And at the beginning we've suggested that we want t to be small as you can afford, on the sample at a high rate. Yeah. So when t is small, then what about R? When t is small, so there's an observation, okay? Or we can make a discussion. We desire t to be, actually I should suggest t should be, no, not t, small t, okay? T should be much smaller than RC. Relatively speaking, we want our sampling rate to be much, sampling period to be much shorter than RC. Otherwise, it wouldn't be a good simulation. It makes sense, right? Otherwise, our Riemann approximation will not be a good one. Okay? So, but when t is much smaller than tau, that means alpha t is much smaller than 1, because alpha is simply 1, because alpha is, because alpha t is simply tau, tt divided by tau. Okay? Now, so if t is much smaller than tau, then alpha t, this factor should be much less than 1. That means R is approximately 1. Okay? Right? That means this radius right here, this radius is close to 1. Okay, close to 1. Inside, smaller than 1, but not much smaller. A good design. When we desire for a good design, to obtain a good design, we know that this factor, this radius should be, it should be smaller than 1, but it should be pretty close to 1. Okay? Close to 1. So that means this low frequency gain should be, when compared to the gain at Nyquist frequency, this maximum gain should be much higher than the minimum gain. Because 1 plus R, because 1 divided by 1 minus R should be large, while 1 divided 1 plus R should be roughly 1/2, right? Yeah. So the low frequency gain should be pretty high relatively to the gain at the Nyquist frequency, okay? And this is good. That's exactly the kind of this behavior, right? This behavior. We want the low frequency gain to be good, while high frequency should be rejected. We want to simulate a low-pass filter, which consists of a capacitor in parallel to a resistor, right? To accomplish this simulation, now we have a difference equation, right? The difference equation here represents a stable system, and the pole is near the unit circle. When the pole is near the unit circle, when the pole is right here, that's our pole, then we know that low frequency gain is going to, the gain at DC is going to be much higher than the gain at Nyquist. Okay, so so this is just to check upon how the system behavior depends on the factor, on the parameter t. Okay, t will control the shape of the magnitude response. It is controlled by t, our sampling period. Okay, yeah. Okay, so this design, now we have talked about the frequency, the magnitude response. I'll finish by talking about the phase response next. Okay, but let me say that this is not. We can do better than this. Okay, this is just our first design. Okay, so how better? So note that here. Note that here, the gain does not go to 0 completely, right? This gain does not go to 0 completely. It's a kind of finite non-zero gain right here at our highest frequency. So that means that actually when we simulate that this system actually does not completely reject any frequency, low or high, right? Low frequency has a high gain, but high frequency has a non-zero. However small it is, the gain is never goes to 0. Okay, at our highest frequencies. Yeah. So I want to just tell you that later we will show another technique, okay, which also borrow from analog. There are some better techniques which ensure that the gain goes all the way to 0 at Nyquist, okay, while having a low-pass behavior, and it then just monotonically decrease. Oh, yeah, bad habit. Now, there is some other technique that we can use to ensure that the frequency, the gain decrease all the way to 0, while the gain monotonically decreases. Okay, so and this other technique, to understand that, we need to introduce bilinear transformation, which will be our next topic. Okay, we need to introduce bilinear transformation, which is a technique to borrow from analog design. Okay, this is actually a transformation between Laplace S and the Z transform. S for continuous time, Z for discrete time. Yeah. So we'll talk about that. Okay, we'll talk about a sort of a transformation which goes from Laplace to the S domain to Z domain, and by introducing that technique, we can simulate this analog system better, in the sense that the magnitude response goes all the way to 0 at Nyquist frequency. We can ensure that. Okay, but there's some extra background knowledge we need to talk about next time. Okay, next week when we meet. Now we talk about bilinear transformation. Okay, so that's keep in mind this is just a design. No design is perfect, but what's cool about this design is indeed that the magnitude response monotonically decreases. So we don't have a tricky situation of, we don't have anything tricky like having a low pass and then suddenly a sort of a ripple. Here and there, we don't have some ripples. So in that regard, we have a nice property. Okay, this response is monotonically decreasing. It doesn't have any funny shape. It doesn't have any ripple. Okay, and ripple is something that we will encounter when we introduce FIR filters. They almost always have ripples. Okay, so that's a feature of FIR filter. But now we have an IIR filter. How we design right here is an infinite impulse response, IIR. Okay, yeah. So don't worry if you cannot completely understand what I'm talking right now, because these concepts, ripples, monotonically decreasing magnetic response, and these properties, these features will keep coming back. Okay, so there are plenty of time we can keep talking about this. But I just today's one day right after midterm, so I want to kind of share with you kind of a preview of what we will encounter, some features and topics we will encounter in the next few weeks. Right now, FIR with ripples, IIR. In doing that, you need to understand bilinear transformation. Yeah. So next, how about the phase? Can we talk about the phase response? So to understand the phase response, I'm going to introduce geometric interpretation. Okay, geometric interpretation. So again, let's write down our frequency response. H e j omega is a constant Ta divided by 1 minus, let me just say R, okay, e to the minus j omega. Okay, yeah. Right. So therefore, the phase is going to be the phase of a real number, which is 0, minus the phase of 1 minus R e to the minus j omega. Okay, that's the phase. Because when we divide two complex numbers, the phase subtracts, right? We take the difference. Is that clear? When we divide two complex numbers, their magnitude divide, but the phase subtract. Okay, so therefore we have, I wish I draw omega. Okay, so that equals to minus of the phase of this complex number right now. This is where I want to introduce a geometric interpretation. Okay, so the phase response really is this. You need to consider what it means to have 1 minus r times e. We need to consider the angle of this complex number. This is a complex number, right? And we know that complex numbers are what? Are vectors. They have directions, right? So what exactly is 1 minus r times e to the minus j omega? So I invite you to think about, look at this figure. Okay, now I'm going to draw it. So we've understood that our phase response, no, not minus. Our phase response is minus phase of this complex number. And let's take a look of this number. Okay, let's take a look of this number. It's a vector, and what is? So let's consider, for example, this angle. That's an angle, right? That's an angle of omega. Okay, so this is a complex number and is basically r e minus j omega, right? So that's right there. And what is 1 minus that? Now, what is 1 minus that? No, this is this, right? This is this. So 1 minus that is a vector that points from right here. Let me use another color. That points from right here to 1. 1 is also a vector, right? So this is a vector from right here to right here. Okay, that's the vector of 1 minus r e to that, right? That's a vector. And then that's a vector. Then how now we consider its angle, right? Now we consider its angle. What is its angle? Its angle should be, this is a vector and that's its angle. This is its angle. This is our phase response at this frequency. But no, with a minus sign, okay? So with a minus sign. So you know that, keep in mind there's a minus difference, a sign difference. That, okay, minus of that, okay? Okay, so now I want you to think about what happens when the frequency increases from DC to Nyquist, okay? It's like we have an object going around the circle, going round and round around the origin, and its radius is r, okay? So imagine that this is a particle. Okay? When omega increases, I want you to imagine that we have a particle that goes from here and clockwise in that direction. That's what happens to this vector. This is a vector, right? Okay. So this is a particle that goes in the clockwise direction when omega increases. When omega increases, we have a particle that goes this direction. Okay? And then how about this vector in purple? 紫色的这个 vector. This vector in purple, how does it vary as omega increases? Okay? So let's draw a few examples. For example, when at DC, this is that vector. Okay? And when the frequency increases, we get this point. And when it further increases, we get this point, and so on. And then when the frequency increases, and it seems that there is a certain frequency at which this vector is going to be what? It's going to be tangential to this circle inside， 变成是切线了So just really making a mess right here. But it turns out that there should be a certain special frequency that I'm going to denote as omega big M, okay? Now, there's a kind of an interesting frequency when this vector becomes perpendicular to the radius, okay? 会跟这个半径就变成跟 is going to be, we have a right angle right here. But then when omega keeps increasing, this particle keeps going clockwise in that direction. Okay, so now we can draw a few more of this vector. Let's say this is so now we have this vector. When we just increase further, when we increase omega further, is the particle goes right here, and that purple vector becomes this vector in that direction, and then it becomes this vector in that direction, and it becomes this vector, and so on in that direction. Okay, and then now we can finally consider how this angle varies when this particle goes around in the clockwise direction. Okay, that's how we interpret the phase response geometrically. And let me tell you that this cannot be found from the textbook. Okay, the textbook does not tell you this. Okay, this is my own, my own heart. Okay, yeah, this is how I see the phase response is a result of this geometric interpretation. And finally, when the omega reaches Nyquist, we have this frequency. We have this vector, okay? And the angle, you can evaluate the angle. So now, to complete our drawing, so let's first draw the negative of this angle, okay? The angle I've been drawing them in purple, okay? All the purple is 紫色. So let's talk about this angle. This angle, how it varies, how this angle varies as omega increases, okay? So you know that at first the angle is 0, right? Pointing to your right, the angle is 0. And when omega increases, it goes this way, right? It goes more and more positive. Can you see that? When omega increases, this vector goes from flat to a little pointing upward, more upward, or more upward. So it's increasing, right? That angle increases. So let's draw a quick picture. It keeps increasing until the vector becomes tangential to the radius, becomes 切线了, becomes when it reaches the right that frequency of omega n. So there is an interval between 0 frequency and omega n where we see an increasing phase response, like that. And then beyond, once we get past this vary frequency, this frequency of maximum phase, then now, when this particle goes further, what do we have? We have a vector right there, and then a vector with a shallow slope and a smaller angle. The angle becomes smaller. Okay, angle becomes smaller and eventually goes back to 0 at Nyquist. Right. So this is our phase. Sorry for making this mistake again. Yeah, something like that. Okay, a curve. Okay, you have a curve like that. You can expect. This is our phase response from 0 to pi, but wrong. We have the wrong sign, right? So now let's correct the sign. We know that actually the phase response, our phase response right here is upside down. Okay, so we have 0 phase, and then most negative phase, and then the phase goes back to 0. Probably monotonically, based on our geometric interpretation. Okay, now. So we have 1 minute left, but next time I haven't been able to complete this. So why do we? I want to introduce this way of sketching the phase response, because by studying whether the phase is decreasing or increasing, we can talk about an important quantity called group delay. Okay, there's a let me just finish talking this, and I'll tell you more about that. Yeah, there is a quantity called group delay, which is defined by this, which is the negative of the first the phase, the derivative of phase with respect to frequency. Okay, this is phase, this is frequency. So this is a first order derivative of phase against frequency, and we call that a group delay. And the unit of phase divided by frequency, you know that group delay is a time. Phase divided by frequency is the time. Group delay is an amount of time, a delay, okay? Which is a time. And group delay is also, there are ways to show that. Okay, there are ways to show that group delay is the actual energy delay when we deliver a narrow band signal. When we deliver a narrow band signal, let's say that we have a wave packet of carrier frequency and with envelope. It's a narrow band signal, is our input, okay? And it turns out that for any narrow band signal, the system which passes through any LTI system, the group delay tells us how much time is going to, tells us the latency or delay. Group delay is a latency, 是个延迟啊，是个延迟。Group delay is a latency that tells us how much this wave packet is going to be late. It's become late because it's how it's passing through the system. Okay, and there's also the minus sign. Okay, so anyway, so this is kind of a introduction to group delay, important concept. And next time when we meet, I'll tell you more about group delay, and perhaps we have a homework. Computer homework, okay? But group delay is an important quantity, important concept you need to know, and its phase is written as its definition is the first derivative of our phase spectrum against with respect to frequency. Okay, so time is up, and thanks for showing up, and I'll see you on next Wednesday. We will continue the lecture. Okay, thank you.